Talking on Castleman's embedding. Welcome, sir.
Thank you. Thank you. Well, I had not announced the title earlier, but let us see read out now. Maybe at this conference I could have called it on Harshchandra's subquotient theorem. They would have more to do the same, but it's really about Castleman's embedding theorem. What I'm going to do is to give a proof of Castleman's embedding theorem, which I think is simpler than existing proofs in the case of rank 1 groups. 2 weeks ago, I thought I had the proof in general, but I discovered a gap which I was not able to fill up. I will say something about how one can get the higher rank groups as well. It's a very naive approach, and I was surprised it worked. Okay, so let me begin with the notation. This subject always carries a big baggage of notation. One can't help it, I guess. So G connected semi-simple group. K maximal compact. And G the Lie algebra of G. I would also use the same notation for the complexified Lie algebra. Let me recall the Harishchandra module. Well, I'll call it a GK module because Harishchandra may make it, narrow it down for some people, so let me call it simply a GK module. It's a countable dimensional vector space over C, which is the structure of a UG module. This is the enveloping algebra of G. As well as as also representation of K made up of as a direct sum of irreducible continuous finite dimensional representations. So that's what a GK module is, and these are known facts. Yeah, let me also fix the split, maximal split in G and let T be the T beats reasonable. Linear. Sorry?
J is linear.
No, yeah. Do I need G to be linear? For safety, I'll assume that G is linear. It may not be necessary. It may not be, because what has come down to GK rule, so it probably is not necessary, but let me assume it's G linear. So maximum split torus T in G and split and T beats Lie algebra, Lie subalgebra, TB Lie subalgebra corresponding to it. As I said, I will also use the same notation for the complexification as well. And then one fixes on the dual T. Here I'm thinking about the real algebra, but I can't fix an order of the dual. Fix an and let phi be the roots of G with respect to T, phi plus minus positive respectively negative roots, and delta system of simple roots. Let me also denote by n plus for alpha in phi G alpha is the root space. This of course necessarily complex corresponding to alpha, and let me denote by n plus the sum G alpha. As is well known, this is a maximal ad nilpotent Lie subalgebra. And let me also write T, the centralizer of T. Write Z of T is necessarily M plus T, where M is the Lie algebra of a compact group which may be assumed to be subgroup of a compact group M. This may assume to be subgroup of K. And I should say alpha, similarly I'll also put n minus here. The Lie algebra G, this is over R, decomposes as K, Lie algebra K plus T is n plus, as also n plus n minus plus zt Okay, and I also denote by Z, the center of UG. Then what is it? I think I'm done with notation. So I hope as I go along, maybe I'll have to say we'll introduce more notation, but at this point, I'll probably stop this. And one has the Harishchandra homomorphism. What should I call it? Maybe I'll call it H, which goes from Z into, well, one can think of it as going to the center of UZT. Actually, let me put it like this: center of, yeah, UF center of Z.
So T is Cartan substance.
It's for the K plus P decomposition, it is the Cartan subspace. Yes. H onto WC W of GC invariance in this space. Center of ZT is a Cartan subalgebra, and then goes into the Z goes into Cartan subalgebra, which of course is an this you have to go over complex numbers. I hope it doesn't cause too much confusion. I keep using the same notation for real and complex things. So the center of ZT is a Cartan subalgebra of the whole the algebra G, and this mapping is into the complexified thing. This is also complexified. WGC goes into invariance and is a polynomial algebra. On L variables, where L is rank of GC.
So Z is a CFT is not so large.
Sorry?
The center of CFT is not that large.
No, it goes into the Wien group invariance into the center of ZT.
Sorry, first ZT is the centralizer.
ZT is the centralizer, and then I take the center of ZT. It's not ZT, it's the center of ZT, which is the Cartan subalgebra.
No.
Center of ZT is not Cartan subalgebra.
Quasi split, it is
Sorry?
we assume G is quasi split with MAU and not a BN.
No, center of ZT. ZT itself is not. ZT is not abelian.
Yeah, fine.
Oh.
I'm saying the center of ZT is basically the Cartan of M added to T.
Yes,
That's the Cartan.
okay. It's not center of ZT. Okay, sorry. Yeah, thank you. Sorry. Cartan. And this is the Cartan subalgebra. This is the Cartan subalgebra of G. Thank you. That's what I meant. Anyway. Okay. And this is where L is the rank of the complexified G. Rank C, G over C. All this is the notation. This notation fixed. I also have to introduce something more, namely the induced representation. This is start with G and look at the subgroup B corresponding to ZT plus N plus, or let me call it P. That's a minimal parabolic subgroup of G, and one looks at if sigma is a representation of P to this finite dimensional representation. Finite dimensional, let's say, irreducible representation of P. Let me write that trivial on N plus, the group corresponding to N plus. So P to GLB will be a finite dimensional representation, and let I P sigma be the induced representation of sigma, and let I sigma, I don't know what I should call it, let me write, be the representation induced by, this is the representation on some Banach space, and I sigma be the representation induced of G K on K finite vectors of the representation space of I sigma I P sigma is what I call it. So if you look at K finite vectors in the representation space of the induced representation, that turns out to be GK module, K acts on it obviously, and G you'll have to take K finite vectors on that G operates. This is all the background information I need, and Castleman's theorem says any irreducible GK module, well again that representation I should have said is on a complex vector space. Sigma is on a complex GK module admits an injective GK morphism into I P sigma for some sigma. That's the theorem of Castleman. Harshchandra had earlier proved you could realize any irreducible GK module as a subquotient, as a quotient of a submodule, of a quotient of submodule of GK. Castleman proved to prove this theorem. Okay, what I am going to do today is to give a proof of this theorem in the case of rank 1 groups G, and also indicate how it can be generalized using an induction. I don't have the proof completely, but my instinctive feeling is I will be able to make it into a proof. But at this point, I don't have a proof of the general case. Okay, now, so I'm going to confine myself to that's the subject of my talk, rest of my talk. It's known, I suppose due to Castleman, that it suffices to prove the following. That if V is a GK module, V is not equal to n plus V. This is well known that it's not to prove this statement. It's a pure algebraic statement from this point on. So this is what I will prove. So V is a GK module, irreducible GK module, sorry. Irreducible GK module of countable dimension. This is what you need to prove in way. And one of the things, again, well known is the fact that Z, the center, acts via scalars on V if V is irreducible. This is a well known result due to essentially Dixmeyer, and I think some of the younger people may not have seen that, so maybe I'll give a proof because it's easy, but when I read it, for instance, it came to me as a total surprise. It never occurred, this kind of idea I never thought of, so I think I'm going to give a proof of that. It's a very simple-minded thing, but the basic point is that if you take the rational function field in one variable over complex numbers, it has it's a vector space, it has uncountable dimension. That's the only remark that needs to be made. And from that follows for the following reason. The proof of this statement, let f v set of t in Vc such that t the GK module endomorphism. This f is obviously an algebra. And since we assume that V is irreducible, f is a field. Every endomorphism is necessarily an automorphism or zero. So it follows that every element of f is invertible or zero. So f is a field. Over C. Now, C, if f is not translated over C, it has to be C. So, suppose f is translated over C, then f contains C function Cx, which is a function field in one variable x over C. And then V becomes a vector space over Cx. Now Cx has uncountable dimension over C. If you take 1 over x minus alpha for various complex numbers, they are all linearly independent rows. So it has an uncountable dimension. And because it has an uncountable dimension, the vector space V itself is a vector space over C, over this field F, and therefore we will have uncountable dimension over C, which is absurd. Our assumption is it has countable dimension over C. Implies V has uncountable dimension. Sorry, F contains Cx. Cx has a vector space over C has uncountable dimension. Implies V has uncountable dimension. The contradiction. So that means F has algebraic over C, so it coincides with C. So that means every endomorphism which commutes with all operations from G as well as K has to be complex, has to be a scalar. So that means every element of Z has to act as scalar because Z acts as GK module endomorphisms. So get the so-called infinitesimal character of the representation. Probably it didn't give a name for the representation for the GK module. Chi from Z to C. So chi of Z in Z operates, acts on V via chi Z. This is the so-called infinitesimal character of the representation. Okay. All this said, I was next. Okay. So let's start with V irreducible GK module. This implies that V is finitely generated as a n plus module. This is essentially a consequence of the irreducibility of the representation, and you use the proof of the Harshchandra isomorphism to conclude this fact that V is an n plus module. Basically, you fix a vector V which is k finite and look at UG of V. This is written as U n plus into U of T times U of K. This is the Lie algebra of the compact group K. So UGB equals this applied to K. U1 plus UT UK is the entire enveloping algebra by the Poincare-Birkhoff bit theorem. So you find that this is equal to this. And then UKV sits in a, because V is K finite, this sits in a finite dimensional subspace E. And then you have to apply UT and UN plus, but if you look at the Harshchandra homomorphism, what it would say is, if you take a central element, it can be written as something here, something here, something here, and this something here is what gives you the Harshchandra homomorphism. Yeah. So that anything here, of course, keeps this E in itself. Anything here, you get something here, and here you get the subalgebra corresponding to the image of the Harshchandra homomorphism, and which is itself a finite module over this, and that does the job. sorry, this is a module over the image of the Harchandra homomorphism. That's what gets to the theorem. Anyway, I'm going to assume this. These two facts I'm going to assume. Now, let's first look at this case when n plus is abelian. This actually corresponds to the classical cases SON1. In all these cases, in all these rank 1 cases, the n plus turns out to be abelian. And so, our module, GK module.
Repeat the last statement you said
So-
about the rank 1 cases.
Sorry?
Could you repeat the last statement you made about the rank 1 cases?
My hearing is bad.
Repeat the last statement about rank 1.
Yeah?
Can you please repeat the statement that you just made?
I just look at the case when n plus is abelian. That really means G is isomorphic to SON1.
So SUN1.
S1. SUN1, it's a two-step, two-step. There's a G alpha and a G2 alpha. I'm looking at the case when G2 alpha is not a root. And that happens to be the same as looking at SON1. Eventually, I'm going to prove it in general. So, just want to say that I'm looking at the case when n plus is abelian. That it is G equals SON1, some sort of classification, one doesn't have to bother about that. I'm looking at the case when n plus is abelian. Now, I'm looking at V as a UN plus module. It's finitely generated, and UN plus itself in this case is a polynomial algebra because n plus is abelian. V as a UN plus module is Noetherian. It's finitely generated module or Noetherian ring, so it is Noetherian. Now, I have the following lemma. If phi, say E to E, is a endomorphism of a Noetherian module, over a ring R, then if phi is onto, it is also injected. Every surjective endomorphism of a Noetherian module is automatically injected. This is an easy lemma to prove. That's one statement. And the second statement we want to make, which is a consequence of that, is the following. So let me write 1.
R is abelian.
Sorry?
R is commutative. R, the ring R. R, the ring is commutative.
The ring doesn't have to be commutative. I'm going to use the fact it's commutative later. At this point, it doesn't have to commutate. It has to be commutative. And the second statement, the following, that is, if E is Noetherian module over A, and phi E to E is a surjective endomorphism, so is phi restricted to E prime. If E prime is any submodule with phi prime contained in E prime. Once it's surjective on the big module, it's going to be surjective on any submodule which is stable under the endomorphism. This is again easy to prove. It's essentially an exercise for a graduate student. Let's see.
I think there's a word missing. You said so is.
Sorry?
In the statement, you said if it's subjective, then so is the restriction.
Very subjective endomorphism. So is. What you do is, if it's not, you look at the image and pass to the quotient by the image, and then you arrive at a contradiction. Okay, so this is the lemma which is going to be crucial for us. This, and then I will also use the fact that n plus is to get at the theorem. Okay, what I do is the following. Yeah. Let x be an element. Now I am going to the proof of the theorem. So, of the Castleman theorem in the special case. So, x and n plus. And look at, suppose xp equals v. So, v is a Noetherian module over un plus. I am assuming that xv equals v is a surjective. Now, we also have in our situation an element h in T such that bracket hx equals x. The entire n plus is the eigenspace for the Lie algebraic T, and therefore you have an h such that hx equals x, which is what I am going to exploit. So let's pick generators V1, V2, Vn, generators V as a module over un plus. Now, I am assuming that x, notice in this case, maybe I should call it pi x. Pi is the mapping from G to so pi x is an endomorphism of V as a un plus module. Here I am using the fact it's abelian. N plus is abelian, so every element is central in un plus. So pi x is an endomorphism of V. I am assuming pi x is surjective, it's assumption. Which implies, if you look at un plus Vi, pi x, since x itself belongs to un plus, it is stable under un plus, and therefore you find is pi x stable, and therefore pi x of un plus, let me call this V sub I, pi x of Vi equals Vi by the lemma. If it's surjective on the whole module, it's also going to be surjective on any submodule which is stable under that endomorphism. And here any submodule is automatically stable under the element x, because x itself belongs to the ring of homothesis. So pi x Vi equals Vi. Now, this means what? This implies there exists an element Ai in the enveloping algebra of un plus, or rather in the kernel of the augmentation ideal, is the kernel of V1 plus Vi, that is only elements coming from the Lie algebra, and multiples of that, products of that will figure AI is such an element, such that AI Vi equals Vi, because Vi itself has to be in the image of the involved algebra, so you have AI Vi equal to Vi. Now let's look at the element. Let's look at the module V plus V plus V, n copies. On this, this is the n plus module, and you have pi x V1 etc. pi of any element in the Lie algebra. So since I have something pi y in n plus, this pi y Vn is nothing but pi y V1 pi y and once again it's easy to see now because of the definition. X hat is a surjective endomorphism of V direction, and therefore it's injective as well, it's an isomorphism as well. So what you find is, it follows that hence there exists a single Lie in Un plus such that AVI equals Vi for 1 less than I less so. I am just applying the fact that it's surjective. X is a surjective endomorphism. That you conclude that there is a in plus in the kernel of the augmentation ideal, kernel of the augmentation map, AVI equal to Vi. Now this implies A W equal to W for every W in the whole module V, because the VIs are generators, and so any element is a linear combination of the VIs, and by multiplied by some elements in UN plus, all of them commute with X. So you find that AW for every W in W. Now I'll bring in the element H and see what happens in this context. So in particular, HW has to be equal to HW. Other than look at HCAW. This is equal to AHW plus bracket HAW, which is again AW. Which is AHW is HW plus W. Now, sorry?
H bracket A is not A.
Oh, sorry. Yeah, you're right. H bracket AHW plus AW. No, sorry. Some scalar lambda. Let me stick to. Okay, I'll do the following. H. Yeah. Okay. See, the point is that AH, there is some A such that AHW equal to HW. A can be broken up into some of eigenspaces for various things, and one of them will work, and you can pick up that one. Can assume with actually some integer. That one. AHW to take with this. Okay, now let's look at W, HW, exponent. Our module is finitely generated, so the module generated by this over UN plus is already generated by something. So you can assume there exists minimal R such that H power R W equals sigma Bi H power I W 0 less than I less than R, with Bi now apply this fact that it changes the name repeatedly and you will arrive at a contradiction case, and that will prove that the original map multiplication by x cannot be surjective, which is what we wanted, and this proves the case in the case SL2, because there the n plus is one dimensional, you don't have to go further. The general case is essentially handled the same way with some obvious modifications. The whole thing works. You have to start writing everything as sigma ai xi. You know, the element, if you want, the surjectivity says take any vector v, it can be written as sigma ai xi, where xi is a basis for n plus, and ai, which is an abelian thing, and ai are elements in un plus. So, if you do that, essentially the same thing works. I don't want to go into details. It's easy. Completely, as you can see, it's quite elementary, the proof. And this works easily for SYN1. But for other rank 1 groups, one has to do a little trick to get hold of what we want. Here, I will use so what I want to say is this: can reduce the problem other rank 1 groups. First, one can reduce the problem to the case when there is a k fixed vector. If there is no k fixed vector, you form the tensor product with a suitable finite dimensional representation to get a k fixed vector. And then you can work backwards and say if it's true for that module, it's going to be true for this module, and you can assume therefore that there is a k fixed vector. So can reduce the problem to case where there is a k fixed vector. Now, what I do is the following: you have this module V and you have k fixed vector V naught. And we had the compact group, which I think I called M. We call that ZT, the group corresponding to Lie algebra ZT breaks up into M times T, M compact. Now, the idea is this: you look at M invariance in UN plus. This is a commutative algebra, which is of course obvious if if 2 alpha is not a root, it's obvious. But what has essentially happens is this: if you, the only possibility is u1 plus is either simply g alpha or g alpha plus g2 alpha, where alpha is a simple real root or root. Now, if you, the point is, if you take the real points in this, it turns out that M acts doubly transitively. That is, if you take any vector v here and any vector w, you can find a it's a fixed vectors v naught w naught, both non-zero, and then there's a transformation element in the M which takes v naught w naught to vw. Should be a little more careful with norm 1. They are both norm 1 elements. Then you can do that. So, which proves that any invariant polynomial on this vector space is going to be reduced to polynomial in 2 variables. From that, it is easy to see the M invariance is going to be commutative, because one of those 2 polynomials comes from G2 alpha, which is in the center of this n plus. So, one polynomial is going to be in the center, the other is, doesn't matter what it is, and the whole thing is generated by those 2 invariant polynomials. Because of that, M invariance in U1 plus is a commutative subalgebra. In fact, isomorphic to polynomial subalgebra. Notice that this algebra is stable under H, because it's G alpha is entirely an eigenspace, and so is G2 alpha. From that, you see that this M invariance is going to be stable under H and will break up into eigenspaces. Now we are in the commutative algebra, and then what you do here, you start with this V naught and take the look at the set, look at the subspace of M invariant vectors, M fixed vectors in V. That is a subspace which contains V naught, and it contains V naught, and it's stable. It's going to be stable under M invariance V1 plus, and it's an easy exercise to see it's finitely generated over this M invariance. So we are back in the situation of a commutative Noetherian ring. This subspace is obviously invariant under, stable under M invariance in U1 plus, and it's also finitely generated, as you can easily see. You take a finite number of generators, transform that by you can also get any vector of this you can get as a transform by U1 plus by some vector, one of a finite number of vectors, and then average the element over K, and you will get what you want. So, and then the rest of the proof follows whatever I have done in the case of when U1 plus is abelian. So the crucial ingredient is that it is stable under H, and this argument which I did not work out completely is the same. It gives you what you want. So that covers the context. In the rank greater than 1 case, as I said, I don't quite have a proof, but I indicate a strategy which eventually should work. Once again, I'll assume that there is a K fixed vector, capital K fixed vector, and so let me illustrate it by an example like SL and R. What you do is you look at the maximal parabolic, which looks like this, and one look at V and look at, let me call this, say U plus and U plus V. You suppose you are able to prove this. Once you prove this, you can pass the quotient V by U plus V, and then it becomes a module over SLN minus 1, which is rank 1 less. Okay. It becomes a module over the rest. Because this U plus is an ideal in the parabolic group, and therefore U plus V is stable under the bigger one, and you can simply restrict, and then it becomes a module over the SLN minus 1, and then induction takes over. That would be. But of course, this is the crucial thing to prove. And I have not been able to quite get at that, but I'll tell you why I think it's highly plausible. The point is this: you look at V and look at, let V the set of submodules not containing V naught. The k-fix vector, as one knows, the k-fix vector is k-fix vector space is one dimensional, so this is a unique vector up to scalar, such that the whole module is generated by that element. So let M be the set of submodules not containing V naught. Suppose it's non-empty, then John's lemma clearly tells you there is a maximal element. If non-empty, apply John's lemma, maximal element, maximal GK module, set of GK submodules not containing, actually irreducible implies this anyway. Yeah, sorry, M be the set of G1K submodules. G1 is this SLN minus 1. Look at the set of G1K submodules, G1K1, it will be the set of submodules not containing V naught. If not empty, John's lemma replies there exists a maximal element. Pass the quotient by the maximal element. Pass the quotient by the maximal element. You get a G1K module which is irreducible. That's a big action. You see, I'm sorry, a priori finitely generated, but you can reduce it further to the case when it's irreducible. Once it's finitely generated, you can pass the further quotient and get something irreducible. So, but one does not know that this family is, why does one claim that this family is non-empty? The family is non-empty because if every module contains V naught, every submodule contains V naught, what of this? Sorry. Yeah, every submodule contains V naught. Every G1 submodule contains every G1 submodule contains V naught. That would be irreducible. Any submodule will have to contain it, contain V naught. It means it's irreducible under G1. Okay, under the submodule G1, induction takes over again. That's the so. But yeah, induction takes over. But what you get is going to be in the case when the V itself becomes a G1 submodule. That cannot be the case. I have not been able to fix that. But suppose it is, then by induction hypothesis you take the maximal nilpotent ideal in G1. Apply it to V, the image is different from V. So you get a large unipotent group which does not map V surjectively onto V. N, if you call N plus prime, N1 plus max nilpotent in G1, then what you find is, by induction hypothesis, you find that n plus V is not equal to V. N plus 1V is not equal to V. N plus 1V is a large chunk. If you can add one more element to that, you will capture the whole thing. It looks like feasible, but I have not been able to fix it till now. But it looks very likely that one can fix that, and then induction will work. Well, I think that's all I want to say. Thank you for listening.
Any questions or comments?
I mean, you still have hopes this will give a proof of your conjecture of...
My conjecture?
The Rachner thing.
Well, you're talking about a completely different thing. Okay. See, for a long time, I was hoping to prove Rachner's theorem using representation theory. Basically, start with a measure on G mod gamma. Let's assume for a moment G mod gamma is compact. It decomposes into irreducible representation, direct sum, and restrict your measure to each one of those singularity vectors in each, or continuous functions in each one of those, which of course therefore gives you linear form on k finite, z finite vectors, which can be embedded in the principal series. So basically you can transform this measure into some kind of distribution on G mod P. Vector bundles, the distribution on vector bundles on G mod P. That's, you can convert them. And using that, I thought I could get a proof. The only thing I could do was to, in the case when the unipotent group is a Horst cycle, I could prove that. But couldn't make much progress about that. In fact, that is why I came to this business. When I tried to prove that, Castleman's theorem, I have to say something more than Castleman's theorem, which is probably there in Castleman's, but I would like to see that. I want to see, it's not a priori obvious that this linear form on the GK module can be extended to a distribution on G mod P, or the vector bundle on G mod P. This is what I was, this is the reason why I went to do this subject at all. Okay. Well, I still have hopes of, I still have hopes, but they're receding.
Thank you.
No, one of the reasons I want to do it is that it was Rachner's theorem, as you all know, was my conjecture, but after some time my name will disappear clearly. It will only be Rachner's theorem. Even now nobody talks of Raghunathan's conjecture, rightly so. It will be Rachner's theorem along. If I manage to give a proof, maybe they will say Rachner-Raghunathan theorem. This is the hope.
Any other questions or comments? Okay, let us thank Professor Raghunathan again.